Welcome to Saltwater Stories. Imagine, if you will, sinking down, way down beneath the waves, thousands of feet into total darkness.
Pitch black.
Right. And down there, hidden from the sun, there are these huge mountains. I mean, taller than many we have on land.
Absolutely colossal structures.
Yeah.
Formed by, fire and shifting earth, just like continental mountains, but deep underwater.
And they're not just empty rock. They're often these incredible hot spots, just teeming with life right in the middle of the deep sea.
It's this hidden world, isn't it? One of the last big frontiers on Earth, really. We're only just scratching the surface of understanding them.
Definitely. And they have this specific name, these underwater giants. Today, we're exploring these amazing undersea mountains known as seamounts.
Seamounts, great topic. So much to talk about there.
Yeah, we want to figure out what makes them so special, why they're so important for the ocean, and maybe what the future holds for them.
Okay, so let's start with the basics. What actually is a seamount? I mean, how's it different from just a big hill on the ocean floor?
Good question. The main thing is height. It has to rise pretty steeply, at least 1,000 meters. That's about 3,300 feet from the seabed around it.
A whole kilometer straight up.
Exactly. There are smaller things like knolls and hills, but that 1,000-meter mark is the key. That makes it a seamount.
Right, that significant height is what sets them apart. And most are volcanic, aren't they? Built from lava.
Yeah, which means they've got this hard, rocky surface.
And that's critical down there because so much of the deep sea floor is just soft mud,
Right. So things need something solid to grab onto.
Precisely. Things like deep sea corals and sponges, they need that hard volcanic rock base to settle and grow. It's prime real estate.
Interesting. And I read about a special kind, gyos, or table mount.
Yes, they're fascinating. They're basically seamounts, but, they have these distinct flat tops.
Flat tops, how does that happen?
Well, the idea is that there were once volcanoes that actually grew tall enough to poke above the sea surface, becoming islands. And while they were islands, waves, just battered them constantly, eroding the tops completely flat.
Like a natural haircut?
Kind of. And then over millions of years, the tectonic plate they were sitting on moved. They cooled down, got denser, and eventually sank back beneath the waves, taking their flat tops with them.
Wow. So they started pointy and ended up flat and deep?
Exactly. And you find clues, like fossils of shallow water corals, or even rounded beach-like pebbles, right on top of these deep, deep guyotes.
Incredible, like little time capsules.
Totally. They tell us about past sea levels, plate movements, really cool stuff.
So the shape itself, whether it's pointy like a cone or flat like a guyot, actually matters for what lives there.
Oh, absolutely. A steep peak interacts with currents totally differently than a wide, flat top. That physical difference creates all sorts of little niches, different habitats, helps boost the variety of life.
Okay, so we get the structure, but how do these massive things actually form down there?
Right. It's almost always volcanic forces tied to what's happening deep inside the earth. There are sort of three main ways they get built up.
Okay, what's the first one? Something about hotspots.
Yeah, volcanic hotspots. Think of them like blowtorches fixed deep in the Earth's mantle, sending up plumes of extra hot material.
Okay, a fixed blowtorch.
And the Earth's tectonic plates are sliding slowly over the top of these hotspots. When a plate is over the hotspot, magma punches through the crust and erupts onto the seafloor.
Building a mountain layer by layer?
Exactly. Then, as the plate keeps moving, it carries that newly formed volcano away from the fixed hotspot. It cools, stops erupting.
And a new volcano starts forming over the hotspot behind it.
Precisely. You get this chain of volcanoes like beads on a string. Yeah. The oldest ones are furthest from the active spot. The classic example is the Hawaiian Emperor chain in the Pacific.
Hawaii, right.
Yeah, it stretches for thousands of miles, showing exactly how the Pacific plate moved over that hotspot. There's even an active underwater volcano, Kamaho'okanaloa, still growing over it near the Big Island.
Like geological breadcrumbs. That's amazing. What's another way?
Plate boundaries, where the plates are actually pulling apart. Mid-ocean ridges.
Like the big seam down the middle of the Atlantic.
Exactly like the Mid-Atlantic Ridge. As the plates separate, magma wells up from below to fill the gap, creating new seafloor. And all along that ridge, you get tons of volcanic activity building smaller volcanoes and seamounts. It's why those ridges are so rugged.
Okay, pulling apart. And the third way?
Where plates collide. Specifically where one plate dives underneath another, that's called a subduction zone.
Right.
As that descending plate goes deeper, it heats up and releases water, which causes the mantle rock above it to melt.
Creating magma.
Yep, and that magma rises to the surface and erupts. This often forms volcanic arcs, chains of volcanoes, sometimes islands, sometimes underwater seamounts, usually running parallel to the trench where the plate is diving down.
Like the Aleutian Islands.
Perfect example. That whole chain includes lots of seamounts formed by subduction.
So hotspots, ridges, subduction zones. It's all magma coming up somehow.
Yeah.
And I guess how it forms affects how big it gets, how isolated it is.
For sure. And how long it lasts. All that impacts the kind of life that eventually sets up shop there. Even the type of lava can give clues about where the magma came from deep inside the earth.
Mind-blowing stuff. So given all that, where do we actually find these things? Are they just dotted around randomly?
Well, they're found in basically every major ocean basin, Arctic, Antarctic, you name it. But they're not, like, evenly spread. They often cluster together.
In those chains we talked about.
Yeah, either in chains from hotspots or arcs, or sometimes just in big groups or provinces.
And I heard the Pacific Ocean has way more than others.
Yes, yeah. By far the most seamounts are in the Pacific.
Yeah.
It's just so huge, and it's got tons of hotspots and active plate boundaries.
Do we even know how many there are, like, roughly?
The estimates are pretty staggering. Probably over 100,000 seamounts that meet that 1,000-meter height requirement.
100,000?
And if you count smaller hills and knolls, the number just balloons into the millions.
Wow. 100,000 underwater mountains most people haven't even heard of.
And here's the kicker. We've explored, like biologically in any real detail, probably less than 0.1% of them.
Less than 1/10 of 1%. That's basically nothing.
It really puts it in perspective, doesn't it? It's a massive frontier for discovery right here on our own planet. Every single unexplored seamount could hold new species, new geology.
And they help track plate tectonics too, you said.
Yeah, those long chains are direct evidence of how plates have moved over millions of years. Super important for geology.
Okay, so they're not just sitting there passively. They actually interact with the ocean currents, right? How does that work?
This is absolutely crucial for understanding why they're so full of life. Imagine a big ocean current flowing along the deep sea floor. When it hits a massive obstacle like a seamount.
It has to go around or over it.
Exactly. And when it's forced to go up and over, the flow speeds up considerably, especially near the top and on the sides.
Like water squeezing through a narrower gap.
Kind of, yeah. And that faster current acts like a bit of a street sweeper. It clears away all the fine, loose sediment.
Leaving the bare rock exposed.
Precisely. Which, as we said, is exactly what corals, sponges, and other attached life needs. It provides that clean, hard surface.
Okay, so clean rocks. But you also mentioned upwelling.
Right. This is maybe the most important effect. As that current flows up the seamount slope, it physically pushes deeper water upwards towards the shallower parts of the mountain, maybe even near the surface.
And deep water has more nutrients.
Typically, yes. Deep ocean water is often rich in nutrients like nitrates and phosphates that are usually pretty scarce up in the sunlit zone where phytoplankton live.
So the seamount is like a giant scoop, bringing up fertilizer from the deep.
That's a fantastic analogy. Yeah. If that nutrient-rich water gets high enough to reach the sunlight, boom, you can get blooms of phytoplankton, the base of the food web.
Which feeds everything else. They call that seamount-induced chlorophyll enrichment.
That's the term.
Yeah.
SICE.
Yeah.
Creates a local patch of higher productivity.
And the currents do other weird things, like swirls.
They do. The flow over and around the seamount can create complex eddies and swirls downstream. And sometimes, right over the summit, you can get these stable, rotating water masses called Taylor columns.
Taylor columns, what do they do?
They can kind of trap water right there above the seamount. Imagine a spinning top made of water sitting over the peak.
Okay.
This trapped water can concentrate things, food particles drifting by, nutrients, even tiny larvae of marine animals. It keeps resources from just washing away.
So you've got strong currents cleaning the rocks, upwelling, bringing up nutrients, and these spinning traps holding onto food and larvae. It sounds like a perfect storm for life.
It absolutely is. It creates this really dynamic, complex environment. That's why seamounts are often called oases of life in the deep sea. Compared to the flat, often pretty empty plains around them, they're just packed with life and diversity.
So who are the main characters in this oasis?
The real stars, the foundation, are usually deep-sea corals and sponges. They're what we call ecosystem engineers.
Meaning they build the habitat?
Exactly. They need that hard rock, and then they grow into these amazing, complex, three-dimensional structures. Think branches, fans, bushes, huge vases.
Like underwater forests, but made of animals?
That's a perfect way to put it. Animal forests.
Yeah.
And these structures become homes, hiding places, feeding spots for tons of other creatures.
Like what?
Oh, all sorts. Crabs, shrimp, lobsters, brittle stars, sea stars, snails, clams, and lots and lots of fish, including some valuable ones like orange roughy, alfonsino, pelagic armorhead.
And it's not just the stuff living right on the seamount.
No way. The sheer amount of life attracts bigger visitors too. The megafauna, whales, dolphins, sharks, big tuna, billfish, sea turtles, they often gather around seamounts.
Why? Just for the food.
That's the main theory, yeah. It's a concentrated buffet compared to the open ocean. Seabirds also congregate above, diving for fish near the surface.
Even the tiny stuff is unique. Microbes.
Yep. Even the mud and the crusts on the rocks have their own special communities of bacteria and archaea doing important jobs like cycling nutrients. And sometimes, well, sometimes things get really weird.
How so?
On active volcanic seamounts, you might find hydrothermal vents or cold seeps, places where chemicals are leaking out from inside the earth.
Ah, life based on chemistry, not sunlight.
Exactly. Chemosynthesis. You get these specialized bacteria that eat things like hydrogen sulfide, and they form the base of a whole separate food web. Giant tube worms, weird clams, specialized crabs. Totally different from the coral gardens maybe just nearby.
Two ecosystems side by side.
Potentially, yeah.
Really?
It just shows the variety. And because we've explored so few, the potential for finding completely new species is just immense. Every expedition seems to turn up something potentially new.
It's incredible. And thinking about those animal forests, you said deep-sea corals grow incredibly slowly.
Painfully slowly. We're talking growth rates of millimeters, sometimes even less, per year. Some of these corals can live for hundreds, even thousands of years.
Thousands. Like older than ancient civilizations.
Some of them, yes.
Yeah.
So those complex, beautiful animal forests take an extraordinarily long time to build up. Centuries. Millennia.
That slow growth really matters when we think about damage, doesn't it? Which brings up another question that are the species found there totally unique, like only found on that one seamount?
The endemism question. Yeah, that's been a big debate. The initial thought, the sort of seamount endemicity hypothesis, was yes, they're like isolated islands, so they should have lots of unique species endemics.
Makes sense, like the Galapagos finches or something.
Right. But as we've explored more, the picture's gotten a bit more complicated. While there are definitely some species that seem restricted to certain seamounts or chains, especially things that don't travel far as babies,
Okay.
it turns out many, maybe even most of the species found on seamounts are also found in other deep-sea places, like the slopes of continents or along mid-ocean ridges.
So not quite Galapagos Islands everywhere.
Not in terms of purely unique species lists, no. But then there's this idea of ecological endemism,
Meaning?
meaning even if the individual species aren't unique, the way they come together on a particular seamount, the specific mix of species, how abundant they are, how they interact, that community structure, can be unique to that seamount environment.
Ah, so the community is unique even if the players aren't always exclusive.
Exactly. It's a subtle but important distinction. The ecological role and the community dynamics are special.
Got it. And do seamounts help species get around the ocean, like connecting populations?
They can, yeah. They can act like stepping stones, especially if they're in a chain. Imagine larvae drifting in the current.
They might bump into a seamount, settle down, grow up.
Reproduce, and then their larvae drift off towards the next seamount in the chain. It can help bridge huge gaps of open ocean that might otherwise be barriers.
Like a series of safe havens?
It can work like that, but it's not guaranteed. It depends on, how far apart the seamounts are, how strong the currents are, how long the larvae can survive drifting. For some species, a chain might be a highway. For others, it might still be a barrier if the gaps are too big.
And sea level changes in the past would have affected this too.
Oh, hugely. During ice ages, when sea level was much lower, some seamounts that are deep today would have been much shallower, maybe even islands. That would have totally changed the connectivity patterns back then.
Right. Okay, let's circle back to the oasis idea. Why is there so much food there? We talked about upwelling, bringing nutrients.
Yep, that's key for boosting the basic production, the phytoplankton, up top sometimes.
But there's also this trophic focusing. Sounds fancy.
It just means the seamount helps concentrate food that's already floating around. One cool way is by trapping creatures doing the daily vertical migration.
The DVM, that's the zooplankton going up at night, down during the day.
Exactly. Millions of tiny animals making that journey. If they migrate down during the day and run into the side or top of a seamount,
They get stuck.
well, they get concentrated there, making them easy pickings for predators living on the seamount. It's like a free delivery service.
Okay. And the other part is?
Benthic pelagic coupling. That just means linking the bottom benthic with the water column, pelagic. Those dense fields of corals and sponges, they're filter feeders.
Right, straining food out of the water.
Constantly. They filter huge amounts of water flowing past, grabbing tiny food particles, plankton, bits of debris. They take energy out of the water column and turn it into their own bodies, making it available to the creatures living on the bottom.
So they're like living nets capturing food for the whole neighborhood.
That's a great way to think about it, yeah. And all this concentrated food from upwelling, DVM trapping, filter feeding supports the whole food web. Plankton eaters, fish eating them, bigger predators eating the fish.
Yeah.
Right up to the sharks and whales.
Does the main food source differ between seamounts?
It can, yeah. Depends how deep the seamount is, where it is, how productive the water above is. Some might rely more on local production from upwelling, others more on trapping food drifting by. But those filter feeders are almost always super important.
Okay, stepping back again. We see their amazing ecosystems, but why do they matter? Like for the whole ocean, globally?
They have several big roles. We mentioned the stepping stone idea helping connect populations, which is vital for genetic health and resilience.
Right, and the foraging hotspots for the big guys.
Definitely. Whether it's just the sheer amount of food, or maybe they use them for navigation, or even as meeting places, migratory animals really key in on seamounts, especially shallower ones.
Not just a restaurant, maybe a landmark too.
Could be. And on an even bigger scale, if you think about all 100,000 plus seamounts scattered across the ocean, collectively, they have a real impact on ocean physics.
How so?
They disrupt currents, they cause mixing between different water layers, they influence how heat and nutrients get moved around entire ocean basins. They're not just bumps, they actively stir the pot.
They can even change water chemistry.
Yeah, that's fascinating. As water flows over and through these biologically packed areas, the processes happening there, all the respiration, nutrient uptake, can actually change the chemical signature of that water mass. They can influence regional carbon cycles, oxygen levels. They're like biogeochemical reactors.
Wow. Okay, so clearly vital.
Oh.
But they're facing threats, right? Despite being so remote.
Sadly, yes, big threats. And remember that super slow growth, that makes them incredibly vulnerable to damage. Recovery takes centuries, if it happens at all.
And the biggest direct threat mentioned is fishing.
Specifically, destructive fishing, especially bottom trawling. That's dragging huge, heavy nets right across the seafloor.
On these delicate coral gardens.
Exactly. The gear just pulverizes everything in its path. Corals, sponges, habitats built over thousands of years gone. It's catastrophic habitat destruction. Plus, it catches loads of non-target species, stirs up sediment. It's really bad news for seamounts.
And it happens because the fish they want are on the seamounts.
Precisely. Seamounts attract fish. So they attract the fishing boats, sometimes using this incredibly damaging gear.
Okay, that's grim. What about deep sea mining? That's becoming a thing.
It is. There's a lot of interest because seamounts can have these crusts rich in valuable metals like cobalt, nickel, manganese, plus sulfide deposits with copper, gold, zinc.
Metals needed for batteries and tech.
Often, yeah,
Yeah.
part of the drive. But the potential impacts are, well, severe.
Oh.
Direct impact is obvious.
Mm-hmm.
You're literally scraping off or digging up the seafloor, complete removal of the habitat and everything living there, permanent change to the seamount's surface.
And indirect effects, too.
Oh, yeah.
Yeah.
Mining operations would likely create huge plumes of sediment that could drift for miles, smothering organisms far away. There's potential release of toxins from the disturbed rock, noise pollution, light pollution in a dark world.
And mining is maybe worse than trawling because it removes the rock itself.
That's a key point. Trawling destroys the structures on the rock. Mining removes the rock, the foundation itself. It's potentially much more irreversible. And often, the areas targeted for mining are the same places with unique vent ecosystems or these really rich biological crusts.
A direct conflict. And the irony of damaging ecosystems for green tech mineral.
It's a major dilemma being debated right now.
And then there's the overarching threat, climate change.
Yeah, that affects everything, including seamounts. The water's warming, which stresses cold water species. It's becoming more acidic as it absorbs CO2, which is terrible for anything building a calcium carbonate skeleton like corals.
Making them weaker, harder to grow.
Exactly. Plus, oxygen levels are dropping in some areas, deoxygenation. And changes in currents of surface production could affect their food supply.
And climate change just makes it harder for them to cope with the fishing and mining pressures.
Absolutely. It reduces their resilience. An ecosystem stressed by warming and acidification is much less likely to recover from being trawled or mined.
So Besides the ecological value, there's economic interest too. You mentioned the fish and mineral.
Right. Fisheries, like for orange ruffy, have been economically important, but they often follow this classic boom and bust pattern.
Fish hard, deplete the stock, move on.
Pretty much. Because the fish grow so slowly and reproduce late, the populations just can't sustain heavy fishing. You get serial depletion, fish out one seamount, move to the next. Managing these fisheries, especially in international waters, is incredibly challenging.
And the minerals are valuable, but mining isn't really happening yet.
Mostly exploration and technological development phase. The big hurdle is the lack of regulations for mining in international waters, although that's being worked on. But the environmental concerns are huge and haven't gone away.
What about value from the life itself, like finding new medicine?
Bioprospecting, yeah, marine genetic resources. The unique life on seamounts, adapted to extreme conditions, could definitely hold chemical compounds useful for drugs, cosmetics, industrial applications. There's potential value there.
But that raises questions too, right? Like, who owns it?
Big questions, especially in international waters, the area beyond national jurisdiction. Who owns those genetic resources? How should benefits be shared if a discovery is made? The new High Seas Treaty, the BBNJ Agreement, is trying to tackle exactly these issues.
And mining could destroy potential cures before we find them.
That's the risk, yes. Destroying biodiversity before we even understand its potential value.
And finally, there are the values that don't have a price tag. Ecosystem services.
Exactly. Supporting biodiversity, cycling nutrients, influencing currents and climate, the sheer scientific and cultural value of knowing these places exist. These are incredibly important services.
But hard to put a dollar figure on.
Very hard. And because of that, they often get overlooked when decisions are made purely based on the economics of fishing or mining. The long-term value of a healthy, functioning ecosystem gets sidelined.
Wow. Well, we have certainly explored a lot today. From figuring out what these giant underwater mountains are, how volcanoes build them,
To how they sculpt the currents and create these amazing oases, these animal forests bursting with life.
yeah, acting as stepping stones across oceans, feeding grounds for whales and tuna, but also facing these really serious threats from trawling, potential mining, and climate change.
And the ongoing debate about their resources versus their conservation, it's complex.
But it all comes back to how little we still know. I mean, less than 0.1% explored in detail. That's just staggering.
So much mystery still down there.
It really is. Which leaves us with a big thought, doesn't it? Given how incredibly rich and important these seamount ecosystems are, but also how vulnerable they are and how much pressure they're facing. How do we make the right choices? How do we balance using the resources they might offer with protecting the unique life they hold we're still only just beginning to discover? What's the right path forward for these incredible, remote, yet vital parts of our planet?
That is the crucial question for the future of our deep oceans.
Thank you so much for joining us on this exploration of the world of seamounts. We really appreciate you learning along with us.
See you next time.